We are going to solve a kinematics problem, where the input data is the graphical record of the velocities of a particle. This problem is designed to incorporate many aspects, such as handling and converting units, solving linear equations, and calculating the intersection points of the graphs with the coordinate axes. As previously mentioned, the only available input data will be a graph that provides the velocity records of a particle moving along a straight path. Without further ado, let's see the problem statement. The velocity of a particle is shown in the given graph. A. Determine the maximum velocity and acceleration. B. Determine the farthest distance the particle was from the starting point. Let's solve part A. For this, we see that we have a velocity graph, and the velocity at time t equals 0 is 0. And the maximum velocity is the peak of the graph, which corresponds to the absolute maximum. This peak is reached at time t equals 6 seconds, and its corresponding speed value is 60 kilometers per hour. In this way, we have solved part of what is asked in section A of the problem. To do this, we must recall the differential form of the equation for acceleration, which is the derivative of velocity with respect to time. To complete part A, let's return to the velocity graph. Note that, since the sections are linear, it might be simpler to use a trigonometric and algebraic approach. We know that acceleration is the derivative of velocity with respect to time, and considering that the geometric definition of the derivative of a function is the slope of a tangent line to a point on a graph, in this case, since we are dealing with linear graphs, the desired slope is the slope of the respective section. Therefore, this differential definition becomes a ratio between the change in velocity and the corresponding time interval. Or, equivalently, the difference between the final velocity and the initial velocity divided by the time interval over which the change in velocity occurs. For example, in the first segment, the velocity changes from 0 to 30 kilometers per hour over 2 seconds. In our equation, the final velocity will be 30 kilometers per hour, and the initial velocity will be 0. The denominator is a time interval of 2 seconds because the particle starts its motion at t equals 0, and by the time the particle reaches its final velocity of 30 kilometers per hour, 2 seconds have elapsed. This leaves us with a ratio, but with incompatible units. Let's resolve this. We'll convert the units so that we have our expressions in terms of meters and seconds only. Since the denominator is already in seconds, we will convert the velocity of 30 kilometers per hour to meters per second. By substituting kilometers with 1,000 meters and hours with 3,600 seconds, and then multiplying by 30, we obtain a velocity of 8.33 meters per second. Returning to the expression for acceleration, we find that the acceleration in this segment is constant at 4.17 meters per second squared. This means that the velocity increases by 4.17 meters per second every second. We can plot this value to keep better track of the acceleration. It is worth noting that the acceleration is constant in the first segment, meaning it does not vary during the first 2 seconds. To obtain a better approximation, it could be very useful to identify all the vertices of the graph to pinpoint the points of change in slope. These points can be obtained from the record or directly from the graph itself. In this way, for the second section, and following the same steps as in the first segment, an acceleration of 2.08 meters per second squared is obtained. Note that this acceleration is also constant. We record this new acceleration on the same plane where the acceleration for the first segment was graphed. Similarly, we find the acceleration for the third segment. Note that in this case, the slope is negative and is minus 9.72 meters per second squared. The physical meaning of this value is that for every second that passes, the particle's velocity decreases by 9.72 meters per second. Note that in this segment, the graph crosses the x-axis, where v equals 0. Keep this in mind, as it is important for solving part B. Let's plot this new acceleration on the same graph where the accelerations for the previous segments were plotted. This will help visualize the changes in acceleration across different segments of the motion. In the fourth section, the acceleration remains negative and the velocity begins to decrease, meaning the particle is accelerating in the opposite direction. Essentially, the particle is becoming faster, but in the reverse direction of its initial movement. Let's continue updating the acceleration graph with this new information. This will provide a comprehensive view of how acceleration varies across each segment of the particle's motion. Now we calculate the acceleration for the fifth segment. By completing the acceleration graph in this way, we can see that the maximum acceleration of 4.17 meters per second squared is achieved in the first and last segments. Note that while the negative acceleration in segment 3 has a larger magnitude, it serves to reduce the velocity until it reverses direction. With this, we have solved part A. Now let's proceed to solve part B. Now let's work on part B of the problem. We need to determine the farthest distance from the starting point that the particle reached at any moment during its motion. To do this, let's review the data provided in our velocity graph. Now, let's work on part B of the problem. We need to determine the farthest distance from the starting point that the particle reached at any moment during its motion. To do this, let's review the data provided in our velocity graph. And remember that the differential of position with respect to time is the velocity of the particle. Conveniently, we can make the following arrangement. Now we have an expression for the position of the particle. Since the particle's velocity is represented by a piecewise function, the following equation must be applied to each of the sections. In this definite integral, t-text initial and t-text final are the starting and ending points for each of the intervals. For example, the value of t-text initial for this second section is equal to t-text final value of the previous section. Also, note that in this section, the graph intersects the origin. This point of intersection is the time when the velocity becomes 0 and then continues with negative values. In other words, the particle moves in one direction, starts to decrease its velocity, comes to a momentary stop, and then begins its return, moving back toward its starting point. This point from which it begins its return is the farthest point the particle reached, and is therefore of interest to us. We will again divide the graph into the 5 sections. Each of these sections has an equation as a function of time, which has been calculated previously and is presented below. If you want to know how these equations are derived, you can download the document from the link in the description of this video. You will find this and other necessary topics for solving this problem. To begin, let's calculate the distances traveled in each segment. For the first segment, let's recall the definite integral we discussed earlier. Geometrically, the area under the curve of the segment in question represents the distance traveled in that interval. We already know the function that defines this segment. We then integrate over the time interval from 0 to 2 seconds. We obtain from this integral a distance of 30 kilometers, seconds per hour. Now let's look at the second segment. Following the same steps and knowing the function that defines the line, we integrate this time over the interval from 2 to 6 seconds, obtaining a distance of 180 kilometers, seconds per hour. Note that, as expected, the end time of the previous interval is the start time of this interval. In this case, it is necessary to find the intersection point of this segment with the x-axis. Let's call this point TF, while the lower limit of the definite integral will be the end limit of the previous segment. It is straightforward to find TF by setting the equation of the line for this section to 0. That is, finding the moment when the velocity becomes 0. This occurs at t equals 7.71 seconds. Now we have the limits of the integral. By varying the limits of integration from 6 to 7.71 seconds, solving this integral gives us the total distance traveled is obtained by summing the distances traveled in each time interval across all segments. For the first segment, 30 kilometers, seconds per hour. For the second segment, 180 kilometers, seconds per hour. For the third segment, 51.70 kilometers, seconds per hour. Summing these three values, we obtain a distance of 261.70 kilometers, seconds per hour. Now, apparently, the units do not seem to be appropriate for distance. However, it is just a matter of unit conversion. Considering that 1 hour is equivalent to 3,600 seconds, we can make this substitution. We can cancel the seconds in the numerator and denominator. This will give us the result in kilometers. We can cancel the seconds in the numerator and denominator. This will give us the result in kilometers. Upon performing the conversion, we obtain 0.0725 kilometers, which is equivalent to 72.5 kilometers. With this, we have solved the problem in question. For more useful content, stay tuned to us.